Department of Chemical and Biomolecular Engineering at Lamar University. He actually got his bachelor's from Lamar and then his PhD from Texas A&M. And we just had some students who were formerly at Texas A&M up here last week with a club that I advise. Anyway, he did his work in chemical engineering. He's a licensed professional engineer in the state of Texas. He's had 17 years of experience in the refining and petrochemicals industry. So we're talking about oil refining to make gasoline and other products. And he's worked with Phillips Petroleum, Chevron Chemical Company, and Chevron Phillips Chemical Company with extensive hands-on control engineering experience. And so it's really the industrial control systems that he's going to talk about that can be compromised or subverted to cause operational issues, which is a major cybersecurity issue. And hence, that's why we've invited you here, Peyton. So go ahead and take over.
All right, great. Can you see my screen?
Yes.
Okay, well, I'm not assuming that you know much about chemical engineering, so we'll cover a little bit about that. But I'm probably one of the few professors who had on the ground in the control room type experience. And so that's kind of what I'm going to emphasize a little bit here when we look at this operational technology. So the outline, what I'm going to look at first, since I'm not assuming that you're familiar with the hazards, first I'll go through some of the hazards associated with the chemical process industries. And in fact, there was an incident in my own community that I wanted to share with you that we were impacted by. And then look at what the traditional risk mitigations are for those hazards. And that will be including the operational technology of a distributed control system, a DCS, and then safety instrumented systems. And then a little bit about the increasing cybersecurity risk, which I assume a lot of you are probably familiar with. And then the risk mitigation approach that people in the chemical process industry suggest. And then what we do here at Lamar to try to promote awareness of cybersecurity. So first, the hazards. So I'm looking at refining and petrochemicals because that's where I spent most of my time. And so I worked at a refinery in Border, Texas. It's in the Texas Panhandle. And I worked in an ethylene plant here locally in Port Arthur. And not this ethylene plant that you see on the screen. So the photographer took a picture of this thing and said, "Ah, yes, that's a refinery." But no, actually, these are ethylene furnaces. This is a small ethane cracker in Groves, which is just a few miles from where I live. But what you notice here are you have these tanks, you have these furnaces, and then you have these tall columns. These are distillation columns. And so in this ethylene plant, you have a lot of hydrocarbon, a lot of light hydrocarbon. So the potential is if that gets out, then you have the potential for explosion and then fire and even toxic release. And even a small amount, let's say, and I'm calling this small, but 1,000 kilograms of methane, that's something close to about 200 kilograms of TNT equivalent. And so it does not, there's a lot of energy in these hydrocarbons. So what happened locally was a TPC group facility in Port Neches, which is right next to Groves, had an issue. Now this is a facility that they purify the 1,3-butadiene that's produced in the ethane cracker, and they probably take the crude butadiene from the facility I just showed you, in addition to others, and they purify it. They purify it for 1,3-butadiene, which they can use in tires. And the problem with 1,3-butadiene is that it's so susceptible. If you have a dead leg where it's not flowing, it can turn into popcorn polymer and then it can burst the piping. And that's essentially what happened in this unit. They had a fractionator, one of those towers. It lost containment in the one of the piping legs in the bottom of that tower, and the level just escaped. Less than a minute, the entire level escaped. And that was about 30,000 pounds of 1,3-butadiene. To put that in perspective, that's like about 6,000 pounds of TNT. It vaporized and then exploded. This is in, not too far from people's houses and high schools and such. So you had doors blown in, windows shattered. Um, and what I've heard, when I talk to some of the people about cybersecurity, they think, oh, well, it's a chemical plant, just go close a valve. And so I thought I'd show you some valves. This is from the Borger refinery. Number one, the question is, can you get to the valve? Do you know which valve you need to shut? These are just small valves inside the boundary limits of the plant. But if you actually, whenever you shut down a plant and you're trying to isolate it, you have to shut down the boundary limits valves. These are very large valves. And when I was a younger man working as a control engineer, I had, we were shutting down, going for a turnaround, and I went off with a group of 2 other operators to close one of these valves. So let me tell you, it is an exercise. It takes a significant amount of time and effort to shut these valves. That's assuming you can get to it. Now, in the case of this incident, the piping was so heavily damaged by the explosion that you couldn't even shut the valve. The valves were not there, so you couldn't isolate it. And so the fire kept burning. It's not easy to put those things out. And before it was over, you had another 2 additional explosions, 4 additional towers fell. And all you try to do in those situations is try to contain it. And they even, I was evacuated. And you think about it, this happened on the night before Thanksgiving. So everyone in that community, we spent Thanksgiving Day in hotel rooms. And those fires burned for over a month. So that's a significant event there. And you also have the air quality issues because 1,3-butadiene is not very healthy. So the hazards associated with CPI, just to summarize then, the worst thing that could happen is you have a loss of containment from the process equipment. And so if that happens, then you have the vapor cloud explosion possibility, you have the fire that you can't put out, and then you have the toxic release. One level down would be if you just have equipment damage, like a vessel or a compressor gets damaged or a furnace gets burned down. That's less likely to hurt someone, but it will shut down a plant for an extended period of time. 3 to 6 months, you're talking about millions and millions of dollars for these large facilities. And then probably the safest thing that could happen if you had an issue was just an unscheduled shutdown. But even that is going to cost you, just $30,000 just to shut down for a small unit even. So the traditional risk mitigation to try to take care of these problems, because number one, we found that a lot of the fatalities that occurred when these things happened were because you had people located inside the boundary limits of these units, was that we took all non-essential personnel, moved them outside the gates. And so, and that was, certainly pushed by the insurance agencies to try to do that. Example there, when I was at the Borger refinery in the 1990s, they cut over from all pneumatic instruments to this DCS and electronics, and they moved all of their control rooms. All their control rooms used to be right underneath the units. They moved all those control rooms outside, next to an old school, outside the gates. And I say it was an old school because the history was that in 1980, that refinery had a big explosion, and that used to be the town of Phillips, Texas. and it just demolished their industrial area and then demolished a lot of houses there. And so they permanently, Phillips 66 had to buy the land, permanently closed it for residency. And so the school is the only thing left right there next to the control room, and they use it for office buildings now. So the other thing that happened when we tried to get a handle on this was the regulations came out for process safety management. So process safety management of highly hazardous chemicals includes a process hazard analysis as a requirement. It's one of the 14 items of the process safety management regulation. And for process hazard analysis, it's left more or less open, but the two primary tools in the industry I've been in, the big heavy industry, is hazard and operability studies, where you look at process and instrumentation diagram and you try to figure out what are the potential hazards associated with that process. And then the layer protection analysis, which is a technique to go from the hazard to what is the probability that will occur and what mitigations do we need to put in place. Okay, so if you look at these mitigations, they're normally in this order. The first one is the basic process control system. That's a DCS system. So that keeps the process under control. And so like a small plant even will have hundreds, literally hundreds of PID controllers. So a PID controller would be a control loop. So you'd have hundreds of variables controlled by hundreds of different control algorithms that keep the process in bounds. And then if you have issues and you have to shut down, or if you need additional mitigation, you go to something called a safety instrumented system. And that's a separate system that has shutdown systems such that it has instruments that it reads and it says, okay, if you're here, it's unsafe, and it'll shut the unit down. And then above that, you'll have maybe active protection systems like deluge systems. And then after that, passive ones where you might have a passive protection would be like a dike around a tank in case it overflows. And then the final layer is the disaster, the emergency response personnel. So if you have a lot of chemical plants in your area, then the only people, the fire department really can't go out there and try to put the fires out in a chemical plant. It takes the people that are grouped together from the plants themselves. So this is what it looks like. We've got in this case, we've got the basic process control system here. It is a PLC, it has a controller, and it has, like I said, hundreds of these control elements. And then you configure that by this engineering workstation here. And the database for all this system is located in the DCS server, and all the data, the history goes in here. And then separate from that, then you've got this safety instrumented system and a safety workstation that you would use to work with that. Now, initially, like when I started with, or when I went to the Borger refinery in the 90s, this was proprietary operating systems that they were using. Since then, Honeywell looked at that in particular and said, well, we can do a lot. It'd be a lot easier to get people to take care of it and to develop this software if it was Windows. And so, I don't know, we heard they talked to our management as well and said, well, we could do this with fewer people if it was Windows too, to be able to maintain it. And so that's where it went. All these workstations now and these servers, they operate off of Windows. So the modern infrastructure here has basically turned to Windows. Now, not the PLCs, not the actual hardware, but the servers part of it, it's all Windows. And Windows is not something that you can use corporate IT to support. That I know from experience. You have to have special groups that are associated with operations. because you think of IT, you're thinking of 9 to 5 jobs, and this is not a 9 to 5 job. This is a 24/7 operation. So the operators typically rely on the control engineers for that support, and control engineers are chemical engineer. Chemical engineers make the best control engineers in chemical processes. I'll put it that way. So it's easier to teach a chemical engineer the control side than it is to teach a control engineer chemical engineering. But for these systems, the availability is prioritized over security because you need access to that DCS 24/7. If you lose access to it and you can't control your process, and it goes out of control, that's just as bad as somebody taking it out of control for you. Availability is more important than the security at that point. But what's happened in recent years was some of these things like Stuxnet. You probably heard about where they damaged a lot of rotating equipment in Iran, and the reason that was interesting is because that was a completely air-gapped system. There's no way in or out of that system. And the way they got in there was they somehow distributed some USB keys, and someone picked those up and plugged them into the computers, and that's how the software was delivered, apparently. And for that reason, I can tell you, ExxonMobil, which is across the street from us, they don't allow USB keys of any sort in their entire facility, I think, because of that reason. But that's, we have a lot of rotating equipment in the chemical process industries too. And it's very sensitive to the RPMs. If you run it at an RPM where you have what we call a critical RPM, then the vibrations will increase. And it has positive feedback. And so it'll destroy the machine. And so you have a PLC that's set up not to do that. And Stuxnet went and overwrote that machine and made it damage them on purpose. Now, Triton was interesting in that they attacked a triconic system, and a triconic system is a system that we use a lot for our safety instrumented systems in the chemical processing industries. And that was kind of a watershed event, a real eye opener, because if they can get into a triconics and they can shut down your safety instrumented system, then you're basically unprotected. It's unmitigated. The other thing is, since all these systems are Windows based, any 0-day vulnerability you have, you can attack a CPI operating technology system. The other thing is, we can't just let any random Windows patches go on our DCS system. What happens, if you put a patch in and it interferes with your control software, that's just an unacceptable risk. So they are perhaps a little bit slower to patch DCS system. We need to do a risk mitigation. And so to analyze the risk for cybersecurity, we go along the same lines as we did for the process hazard analysis before. For the typical analysis, you look at the risk as a combination of consequence times the frequency. So the consequences, how bad is it? In terms of, are there potential fatalities? What are the loss levels? And then what's the frequency that it would occur? That's how you have your risk. For cybersecurity, the thought is from the chemical process industry that we'll look at it in terms of consequence times likelihood. So likelihood takes the place of frequency, where you have to consider, well, what's the threat? So is it an individual, an organization? Is it a government? What's the vulnerability, the design flaws that might be attacked? And what's the attractiveness? What's the value to a specific facility? So it's a little more nuanced for the cybersecurity. And then what you do is you take a look at your system, and say, well, what would happen if they compromise this engineering workstation or they compromise this safety workstation, then what would be the consequence of that? And this is where if you have, like for the controls, like if there are hundreds of PID controllers in a plant that's operating, then it would be quite easy to change the direction of that control and have every single one of those controls stop functioning. And you cannot run a plant in manual. And so it would shut down. Of course, shutdown may be the best thing. You would rather have a shutdown than a release with fire and explosion, or even better than damaging equipment. So the point is there that you may have someone come in and compromise some of your systems. More likely than not, as in the case of Triton, they probably would make mistakes. And one of the reasons is these systems are extremely complicated. Honestly, if you wanted to try to even damage a piece of equipment, you'd have to know, well, what's the equipment name? What are the tags? And that's very difficult to figure out unless you actually worked at that system, right? So I'm not saying it's easy. It's more likely that they would make a lot of mistakes along the way, and those mistakes would be causing your machine to not work properly or to reboot, or they would make changes that made no sense. And so it's in our best interest to train our process operators so that they can identify that. So they're thinking about that. And so if that sort of thing, if they see it happening, that they can identify it. And in the Triton system, the whoever it was that broke into it actually got pieces of equipment just like that system. But even then, whenever they infiltrated it, they caused it to crash and just shut down the process a few times. The only way they found out that they were being attacked, as a cyber attack, is they took that equipment over to the vendor, and the vendor's the one that told them, "Oh yeah, you are under cyber attack there," because they didn't know it. All they knew that it was crashing. Okay, so we need to think about trying to build awareness of the people who operate the plants, and some of the companies do that. I know that ExxonMobil, they do have that some of those programs. I had a brother that worked there, and but we also, we're trying to promote awareness with the chemical engineers at Lamar University with our unit operations laboratory. So in our unit operations laboratory, we have an industrial DCS. And so we have 3 experiments, and then we've got one group that acts as a process control group. And they try to understand, well, what are the control structures involved? And then once they've done that, and I've given them a tour, then they do a simulated cyber attack, and we see if the other groups can figure out, are they being attacked, number one, because there's a lot of false positives, if you're working on a new system. Are they being attacked? And then if they figure out that they're being attacked, then you have to ask the question, well, what exactly are they doing? And so that's the key. I'll let them interrupt the other groups for just 5 minutes. And if the other group doesn't figure it out in 5 minutes, then they have to let them go. So we've got a flow experiment, a level experiment, and a temperature experiment. This is what our flow experiment looks like. In this diagram, this is typical of a PNID diagram where you would have a square around anything that goes into the DCS. So this would show that I've got actually it's just an indicator. I've got an indicator here, here for these pressures. I've got a flow controller here. This should have a square around it right there. And This is where that group sits. So this is in our unit operations building. So you can see through the window, there's 3 pumps in a row there, and in the foreground here we've got 2 computers, and it really doesn't matter where you log in. If it's a DCS, it's all the same. So you can log into any of the computers in that room and then pull up that unit. So what they do is their job is to operate that unit and get their data off of it. So they'll line up, they'll turn on so line up means they open the appropriate valves, then they'll operate the pumps at different impeller sizes, and then they'll try to tune their PID control loops. So this is what the graphic looks like. This is kind of the type of graphic. This is a screenshot of a graphic. It looks like this is a lot like what a graphic would look like in a plant. So you click on a pump, turn on a pump, click on a controller, and you can make it go to automatic or automatic or manual, and then you can go somewhere and try to tune it. Okay, and so that's what it looks like from that end when the group's doing the experiment. The process control group then goes through, and they have like access to the same tags, so they'll identify the tags with the experiment, and their job is to diagram them into complete control diagrams, and they'll review the additional parameters and then decide how they want to attack it, and they'll simulate attacks and force the operating group to detect it and respond to it. And this is kind of where they sit. They sit these 2 tables operating these 2 machines. Just down the way, this is where the other group was sitting. And so this is an example for the controls for the flow control experiment. These are, they call them control modules inside the DCS. And what this is showing is that I've got a PID loop here. It has a set point that comes in, and then it has an output that, this is from one of my groups, they drew it wrong. Actually, this output goes over here to this auto man, then to the valve, and then this analog input is the flow control. This is the flow indicator from a transmitter that comes into the PID. So the PID has a set point, an output, and a process value. And then there's a lot of configuration things in a PID controller. So one of the things you could do, for example, is you could just inactivate the whole control module. That's fairly easy to do, and then it would just stop working. You can place components in manual, individual components in that control module in manual. If you have that kind of access, it would be easy to misconfigure the PID controllers. You can change the output limits to where the output only goes up to 30%. The valve won't open any higher. Like I said, you could change the control action from direct to reverse or vice versa. And what that would mean would be the controller would try to make a change in exactly the wrong direction. And so if you did that, the controller would have to be shut off and running manually. It'd be pretty useless. It would not hold control. And of course, you can disable digital outputs, you can spoof inputs. You can put things in manual and spoof inputs. So those are the options I gave the control group. Some of the things they did was they seemed to like to shut down the pump while the other group was operating it. So they're also, one of them manipulated a temperature reading, and it took a while. So if you make a temperature read something other than what is coming in from the thermocouple, then the process control is not going to work. And then there was another one where they took away access to a level controller. They were behind them, and in that case, they were sitting right next to each other, so they figured it out pretty quickly because they heard them, I think. Like I said, one of them changed the PID from direct acting to reverse acting. So some of the other things is they changed the an interlock on a pump. So we have a level control pump where I don't want them to ruin the pump. And so there's an interlock with a low level. And so they just turned that interlock on and the pump turned off and the group couldn't turn it back on. Another one changed the high limit output to 60% for the level controller, which means they couldn't control the level anymore. So these are some things that you could do, if you had engineering access in an actual plant. Now, none of these things are really going to cause an explosion, typically. I would say most of them would just cause the unit to shut down. That would be bad enough. But it's some of these things that you're doing here, if you're a control engineer and you make changes, that's one thing. But if you're someone else and you have that access and you make changes, and let's say it's in the middle of the night and all you have are operators there, they have no idea how to change it back. Okay, and if you make enough changes, even a control engineer will be swamped. And for that matter, there are some facilities where there's not even control engineers there. They come from some central location. Most of the time, they're not even assigned. Okay. So in conclusion here, we talked about the hazards associated with the CPI, the explosion, the fire, the toxic release risks. And then traditional risk mitigation includes the distributed control systems and the safety instrumented systems. And those are now Windows-based systems. And so they're more susceptible to attack. And so the chemical process security, cybersecurity risks are increasing. And operational technology for hacking tools, you know how that works. It's once you develop a library of hacks, you can use it over and over again. Those things just get better and better, or worse and worse. And we talked about cybersecurity risk mitigation, and you put it in the context of process hazard analysis. And then what we're doing here is we're trying to promote awareness with the undergraduate process control laboratory module. Okay, and I've got my acknowledgement, and be happy to take any questions.
The floor is open for questions. You can unmute yourself and ask a question. That would be great. So I'll ask a question. I've got several here, but so how can these, let's say they have a group of hacks or an array of hacks. Are there ways where you can develop an array of detection mechanisms so that you can detect the hack and fix it kind of automatically?
I've seen papers talking about using model predictive controllers to try to identify where the process is not behaving as it should. I could see that maybe detecting if someone was trying to change a value, but in general, it's just if someone is most of these measurements, like in the safety instrumented systems, are not used at all in process control, and so you're not going to be able to detect them that way. And so the number of things that you could do to the system are just limitless, really. I think the real thing that's standing in the way of this being easy to do is the fact that every chemical process unit is unique. They're all unique. They're all extremely complicated. And so it would almost take someone who was familiar with that system to do anything, to even figure out what unit or what piece of equipment to attack. I think that's our saving aspect of this. let's see. Yeah, so I was thinking in Border, I noticed, and you notice if you work in a plant that they refer to everything by numbers. So like if they're talking about a unit, they're talking about, oh, those are the 304s or the 405s did this or the 601s or, unit 9, it's like that. And what they told me back then when I worked at Burger was, well, that was a holdover from World War II when they
Mm.
were using, code names and keywords like that for to describe units. And so that's still kind of the way it is. The ICS, ISA naming conventions is still unit number and then letters and then which number is it. So I think that's what's helping us. But the short answer is I couldn't see any way where you could figure out what they're doing beforehand, unless you can see the cybersecurity side of it. You look at the logs, try to figure out if you're being attacked, those sorts of things that you normally do for cybersecurity. I could see that, but as far as what's going on in the control system, then I don't see it easily being detected.
And a related question would be, how accessible are these control systems to the outside? Do you have to be really an insider, or are there ways people um, can get into the system from the outside?
So there are some systems that are available remotely,
Hmm.
control engineers for convenience. Um, but all of them, I would dare say, all of them are connected to the internet in some fashion because your data has to get out to the enterprise system so they can use it there. So it may be difficult to get in, but there is a connection, if you can get through their firewalls. I'm not even sure that it would seem like that would be a company specific thing, a plan to isolate it completely, I guess. But even then, you would have to have backups to get it restarted. You're shutting down at the minimum. There's no reason why a DCS has to be connected to the outside world. There's no reason except for convenience to the process engineers and to the
Hmm.
company. Yeah.
Hmm. I don't want to take all the questions. Do other people have questions they'd like to ask?
I've got a related question. On the picture that you just have, Peyton, there, so you have sensors, I see, right? And you mentioned that, this is primarily for control purposes, and maybe you have what you need in a way. But if you were to kind of observe anomalous behaviors and things that could be a suspect, you may not necessarily be able to tell whether it was an actual attack or what type of attack it is. But I could see right there an opportunity for robbing another way to make use of this. So is this done in the chemical industry in general to use these and some other things to observe anomalous behaviors that could be attacks eventually?
At this point, I would yeah, I don't know of any cases where they do.
Okay.
What I do, like I said, I know there have been papers published on using model predictive control to try to detect it. But on the other hand, most of the time, if you wanted to like if you wanted to destroy a furnace, it's not really that difficult if you know what the tags are and you have access to it. If you shut off feed to that furnace, it's going to heat up, it's going to burn up, and it's going to it probably even rupture tubes. It's not, what you want to turn off, and better if you can turn it off and then not let anybody know that you turned the feed off. Then yeah, I mean that's almost uh, pretty easy to figure out ways to do that. But the hard part would be, I think, um, knowing what pieces of equipment that you're wanting to attack in the first place. You know, that's all proprietary data, you know, for a company, and so they have to get that information. It's not like you're going to have a random hacker that's going to have the understanding and it's going to have the details to where they know specifically what to do. You've got, like I said, you've got hundreds of PID controllers. Which one is it? You know, if you mess around with too many of them, you shut the plant down and they may figure out that you're trying to do something.
Mhm.
Yeah.
Okay.
For the non-ChemE audience, they may understand what you mean by turning off the feed, causing a temperature to increase. And the idea is that, tell me if I'm wrong, but the feed is at a lower temperature, and so it has an automatic cooling effect. You're always heating it up. But if nothing's coming in, you're just heating whatever's there and continuing to supply heat until it starts a fire or boils over or something like that.
Yeah, there was a case, you know, when I was working at this local ethylene plant where they have a steam superheater that's separate from the furnaces. And, you know, so you want to feed superheated steam to your turbines to drive the compressors. Um, and so this steam superheater, for some reason, I don't know what actually happened, but for some reason, the feed got stopped, you know, it got closed off. And so what was odd about it was that, you know, the board operator looked at it and was looking at the temperature of the outlet, you know, the outlet temperature, and it was slowly dropping. It was slowly dropping. Okay. Now, what it wasn't showing was the fact that this thing, you know, and the PID controller was cranking in more fuel gas to heat it up more. But what it wasn't showing was that inside the tubes were getting hotter and hotter, you know, but there's no movement, and so you couldn't tell it from the where the temperature measurement was. And so this, you know, they sent an operator out to look, and it's fairly congested, but you know, he walked out underneath it. There was 3 burners, and then just as soon as he walked back out from underneath that furnace, one of those tubes ruptured, and you had that huge amounts of steam coming out of that thing. You know, so I mean, I've seen it, and it's not like it's hard to tear this stuff up because we tear it up even though we don't want to, right? They almost burn down furnaces all the time. So, not to be, they don't do it intentionally even. Okay.
Yeah, that's a typical problem where, you know, if feed stops, the exit temperature goes down because nothing's, you know, it just can cool, um, and the flow doesn't continue, so you can't see what the real temperature is inside. I've got an idea. We were looking at something with a bioreactor, and we're looking at a digital twin. Is some of that being used for some of this? It seems to me like you could have a digital representation of everything that's going on. And I wondered if you had it here with the historian and the DCS server. Maybe that's not it, but is that something that's being used?
I do know that they, you know, companies I know of use a separate DCS. So like they have the DCS on the unit, and then they have another DCS where they try things out on, and they'll model things. You know, not high fidelity models, although I guess some companies do use high fidelity models. Not, but they'll model them with control type blocks like leads, lags, dead times, you know, first order processes. So they'll model things like that in order to configure their processes in the first place. But as far as matching them, you know, there's real-time optimization applications that are used in refining and petrochemicals, but those are all steady state. I do know of some unsteady state models, but those are in like if you're doing transitions and you're making polymers. So you want to transition from one polymer to the next, then they'll have an unsteady state model for something like that. Yeah. So
Okay. If there's any other questions, go ahead and ask. If not, let's thank our speaker. It's been very informative. I'd like to be in touch with you in the future. If we ended up, I love what you're doing in the lab. If we ended up doing something like that here, that'd be awesome to try to learn from you guys.
Great. Thank you for inviting me. Appreciate it.
Yeah.
Thank
All
you
right.
very much.
Thank you.
So for Cyber students, make sure to fill out the survey, and we will have our last Cyber seminar for the semester 2 weeks from today, April 5th.